Mustufa for his talk. The topic of his talk is AI-powered economic optimization on microgrids.
As I'm sure we've discussed in detail in the last couple of days, microgrids are becoming increasingly important across Pakistan, because of the large-scale integration of solar power happening and commercial and industrial sectors. This transition brings significant challenges. Obviously, there are challenges on the grid side, but also for the industrial power plant owner itself. So, because these systems integrate diverse generation sources from solar PV, grid, captive generation, and in some cases now battery storage as well. And all of these sources have their own characteristics. Everyone wants reliability, and often reliability can conflict with economic considerations. And because of the diverse nature of these sources, traditional design approaches just cannot capture the dynamic behavior of these systems. And therefore, as more businesses adopt microgrids, comprehensive time is telling us that, experience is telling us that comprehensive time series simulation is now becoming essential for making informed design decisions that can balance reliability, cost, sustainability, etc. Now, where does our system fit in and how it tries to solve these problems? So our system, our modeling tool, simulator and optimizer, it addresses 5 fundamental questions that microgrid designers and operators need to answer. So from a technical standpoint, how reliable is the proposed configuration? Economically, what's the true life cycle cost per unit, for example? Operationally, what are the different generation resources utilized throughout the year? And are those being utilized in fashion efficiently? And strategically, what's the optimal implementation phasing for evolving load profiles? Today, we consume 5 megawatt. 3 years down the line, we might consume 15 megawatt. How do we scale up our generation and sources that make up the microgrid to evolve efficiently with our increasing load profile and growth? And also then from a sustainability perspective, what is the environmental impact of various sources and at what capacity do we utilize them? So the power of our approach is that we can address, through our simulation and modeling work, we can address all of these dimensions simultaneously rather than in isolation. I wanted to spend a bit of time just going through the details of our system, because I think as an academic exercise it's probably good for people to understand how we build this sort of thing, this tool, and what are the parameters that we've tried to prioritize when we build it. So what we've tried to do is to build a modular component-based framework designed for flexibility, because we know today we're starting with 4 sources, 5 sources. We'll probably need to add more as time goes along, and so on. So at the top, there's a front-end interface for configuration visualization. Then we'll have the core simulation engine itself, which it implements detailed models of power sources and realistic behaviors, which is probably the most challenging work of all. Their optimization module implements a genetic algorithm to efficiently search the solution space, which can get very large based on how large a microgrid is and how many sources it has. Then, of course, data processing module, which will take inputs from the sort of inputs we have in the system are site-related load data, load profiles, then, of course, data for resources themselves, because obviously for renewable resources, the geology will determine what the renewable potential is. And of course, economic parameters which change all the time. inflation, things like tariffs, etc., etc. So overall, this structure allows us to model virtually any microgrid configuration, no matter pretty much any sources we use in Pakistan. We can efficiently configure them and sort of adapt the application as well to the client needs. Now let's walk through how the simulation process actually works, how our product actually implements the simulation. So the process begins with hourly initialization of load requirements and resource availability. Then for each hour, we implement priority-based dispatch to allocate available generated outcomes. So the user will assign priorities to the sources part of the microgrid, and then for each hour, based on priority, these resources will be used in that manner, and of course, based on the basic physics principles as well. Our best management system, for example, makes intelligent charging and discharging decisions based on system state. Things like failure and fluctuation of load, and as well as failures of sources which are probabilistic. We model these things in a real world environment. And for example, things like equipment outages and sudden changes in renewable output as well are handled in a very realistic manner. So these hourly results are then aggregated into meaningful performance metrics that can ultimately, as you aggregate them upwards, they can become KPIs which you can make decisions on. So that's the process we follow for running one simulation, but our optimization framework is where the power really lies. So we use a genetic algorithm to efficiently explore vast number of possible configurations. So we encode design variables like source types, quantities, implementation timings, commissioning timings as chromosomes, as a fitness function that we have balances. It's kind of an equation that sort of balances multiple objectives like cost with reliability. This can be adapted to client needs, and optimizations work like natural selection, hence the name genetic algorithm. So it starts with diverse configurations, and then it evolves these through selection, crossover, and mutation, just like evolution or genetics works. And over successive generations, this process converges towards solutions that would be almost impossible to find manually. So the case study I'd like to discuss today is for our long-standing client SCCMC, who has gold mine 32 as snow. We've provided services on these gold mines for nearly a decade now, since the start. And despite having a 5 megawatt solar plant, the base generation happens to be diesel. They don't have a grid connection, and there's no gas availability. So at the start of the project, diesel was the only viable, quick source that they could start off with. So what they needed a solution, because of the high cost of diesel, they needed a solution with low upfront investment. Therefore, they preferred things like PPAs over capital expenditure. Reliability is something that's non-negotiable for them because of their dewatering loads that prevent mine flooding, and that's something that is completely non-negotiable for them. What they needed as well was a solution which could be deployed rapidly, and it needed to have high ramp rates, which would maintain stability for mission critical workers. So when they contacted us for this particular requirement, they had already received an offer from a vendor who was offering a PPA, and this was, on the face of it, a very good offer. However, when we simulated the vendor recommended option, which is scenario 1, which combines the existing solar plant with their existing diesel generators, as well as a new solar PV and BESS capacity on a build own operate PPA model, although the pricing on the face of it was very good, the problem was that when we ran it through our simulator, we realized that this configuration would not be able to stop a huge number of critical load interruptions happening for our client, and that would be disastrous for them and actually result in a much higher total cost of ownership for them for the 12-year period that they were envisaging and planning. So what we then did was we used this our microgrid simulator to find an optimum solution for them, which we did. But then when we used which is scenario number 2, and scenario number 3 is we used our genetic optimization module to actually take scenario 2 and plug it in and see if we could actually optimize it further, and that's basically scenario 3, which presents the best outcome for. So we look at each of these in turn. So this is the configuration and the high-level KPIs for scenario number 1, produced by our simulation tool. So the biggest issue with this scenario is that over a 12-year period, critical load interruptions is 128, which is just non-negotiable. That obviously reflects in a very high cost. So our tool actually inputs a number for a client, which is if your critical load is interrupted, what is the cost of that interruption to you? Some clients in the process industry have this number available readily, and these guys did, and that's kind of contributing to the very high average cost per unit, and then of course the low total cost for the year, for the 12 years as well. So scenario 2 is what we came up with using our tool, simulation tool, and obviously the capacity of, so what changed here is that the ratio between the new PV source and the BESS needed to be changed. The vendor had not accounted for the fact that the condition that they had not accounted for the solar output that actually happens in the third desert, and therefore the ratio between BESS and solar needed to be adjusted. So once you did that, we were able to experiment using our tool and come up with numbers, come up with a configuration which could optimize the scenario on critical load interruptions and to a large degree on load shed events, and bring down the average cost to $0.233 per kilowatt hour, as well as bringing down the total cost from 194 something to 138 million for the 12-year period. Now, scenario 2 itself came about after a lot of experimentation, a lot of technical trial, and meeting with the client, etc. And it was kind of beyond the capability of probably any consultant on our team to come up with, or run probably the hundreds of thousands of configurations that you could do if you consider the capacity of the system, the type of sources, as well as when those capacities could be added during the 12-year period that our client was interested in. And so, therefore, that's where our optimization module really shines through, where you feed a set of options to it. So, for example, you feed, these are the sources I'm interested in, these are the ratings and capacity of the sources that I'm interested in, these are the years during which these could be commissioned, during the study period, and a bunch of other parameters, and then you let the system run. You define certain hyperparameters for the search, for the genetic algorithm itself, such as number of generations it should run before it presents an outcome. And once we did that, the scenario presented as the optimum scenario was scenario number 3, in which, as you can see, it provides a staged implementation plan. So you start off with implement 55 megawatt PV plants total, but you start off with year 1 40 megawatt, and then in years 3, 5, and 8 you add 5 megawatt capacities. As the load increases, therefore these capacities are tied up with how the pattern of the load increasing, and similarly for BESS capacity you add them as time goes on. And obviously this then, over the first scenario, which was recommended by the vendor, it was a 37% reduction from the $194 million. It brought down the overall cost to 122, and the average cost from the very high is about 0.3 above dollars per kilowatt hour to 0.2. It also obviously gives you very, very good reliability numbers of 0 and 52. The key number being critical load interruptions needed to be nearly 0, and therefore this is just not achieve that as well. Give a demo of a limited version of our simulator and optimization tool. So this is what it looks like. The first step is to basically configure your sources. So we can configure it, like adjust this, customize this based on what the client needs are, what they're looking for, and what sources they have. In this case, for example, in the SCCMC's case, they had an existing solar PPA of 5 megawatt, which they implemented from the start, hence A1. And they also had captive generators, 9 of them of 1.5 megawatt, and that was essentially the problem. So we can run the simulation to see what this looks like for them, based on their load profile and everything. So these two sources, over a 12-year period, this would give them 7 critical load interruptions. So that's not very bad, although it's a disaster for them when this happens. It will give them a huge number of load shedding events as their load increases. Very high unit cost, and then if you look at these numbers present, most of the cost energy is contributed by diesel generators, therefore most of the cost is also because of diesel generator maintenance, fuel, etc., etc. If you look at what the energy production is, so most of it, by big majority is coming from line shares, coming from diesel generators, which are obviously very expensive, and therefore just the energy, that is the cost contribution. So in terms of cost, solar is a very tiny proportion of the cost, diesel dominating the overall cost, and of course as diesel maintenance and fuel becomes more and more expensive than inflation, the unit cost will continue to rise over the 12-year period. So that's obviously not good, which is why they wanted a solution, and therefore what you do is you kind of end up with looking at this sort of scenario and saying, okay, well, how can we resolve this? And the tool helps you in running simulations again and again to come out with a better strategy of sourcing the power based on the fitness function. What are their KPIs that they want to optimize? And even a human can get to a very good result using a tool like this. So if we combine things like BESS and solar and additional solar power, as well as their existing renewable capacity for a last backup, we'll see that we get a much better KPI numbers. This simulation would need more time to run because the number of sources is very large. We have 19 units of 5 megawatt hour of BESS units. So obviously, as the number of sources it becomes larger, the simulation time increases. Just a minute. There we are. And as you can see, the critical load interruptions are basically gone. This is basically gone as well. The average cost is reduced by a very substantial amount. The cost, total cost has decreased from 201 to 143 million over the 12-year period. And now this starts to look much healthier. Captive DG is occupying a very small amount of the energy contributed, and therefore the cost and renewable sources like the PPA for solar, and because solar is charging less more, therefore that's the contribution. The loss due to interruptions is basically reduced, it's gone, and over a period of time, as you can see, the unit cost as the load increases and BESS and the renewable sources become more and more utilized, the cost continues to decrease. It's important, by the way, to note that this is because it's based on PPA, and inflation was what built into those PPA contracts. So this won't capture the influence of inflation on factors that are not price set as PPAR. And then these are the load shed events. So as load increases over time, in the first few years we don't see any load shed events, but as load increases, we'll see some load. I mean, this is a very small number for an annual thing anyway, but that just shows you the trend of how when these load shed events may happen as load increases over time. But there, importantly, there's no critical load interruptions. I hope the presentation overall and the demo provides a good grounding of, and the case study as well provides a good grounding of where to exist, in what space does it exist, and what problems it can solve. But just to make adequate clarity, we basically our system serves two key application areas we feel. Obviously, firstly, as a microgrid design feasibility analysis tool, it can help clients and consultants assess the economic viability of new installations or upgrades to their power sourcing, so energy sourcing systems, and by optimizing technology selection and implementation phases. It can also, and this is the second use case, it can also, and to be fair, to be honest, more interesting to me personally, is that it can also serve as an energy management system component. So it can use operational data to dynamically optimize dispatch strategies and monitor performance. So both applications leverage obviously the same core technology to support data-driven decisions throughout the life cycle. So same core, two different use cases, one as a design feasibility tool and one as a tool that actually collects real-time data in your microgrid environment and then tells you as a decision support system what configuration should the plant be operating on right now based on the load projection, the current state of all the sources, the current state of your heat and energy assets, etc.